For pneumatic ECS pressurization, we're going to cover them together, and they're pulling elements here out of ATA chapters 21, which is pneumatic, and then 36 ECS pressurization. And so, let's see, here we go. So yeah, pneumatic, ATA 36. You'll also see pneumatic covered in 75. What is 75? Why do I have 75 up there? What falls in the 70s category of engines? So you have engine bleed air. Well, you have bleed air, customer, this is all customer bleed air, but there's the customer bleed air comes from the engine. So there are engine side components, and then there are airframe side. So we're going to focus on the airframe side components. You're doing a lab in turbine engines and systems, probably right around now, that has to deal with looking at the engine side of the customer bleed air. Now, this is still customer or airframe bleed air. Engines also have engine bleed air, which is, or control bleed air to control things like compressor stalls and to provide cooling for the engine and everything like that. That is a separate, that's separate bleed air from the customer or airframe bleed air. Environmental control, ATA 21, is our heating and air conditioning. We just call it environmental control systems because in a transport aircraft, we really don't have a separate heat and air conditioning system. You know, it doesn't, we don't have a vapor cycle air conditioner and a fuel fired heater like we do in a GA aircraft, but rather we take bleed air and we make it hot and cold using a systems of valves and expansion turbines and compressors and heat exchangers. And then pressurization also covered in chapter 21. Because they're so related, you know, all three of these build on one another. Pressurization is going to build on pneumatic and ECS in order to take place. So altogether, these are often referred to as an air management system. If we look at where they fall, kind of throw it all into the airplane. Here's a diagram of a typical twin engine aircraft, just showing kind of the systems. You can see a lot of it's centered right here in the wing root area between the engines. Our engines are our main bleed sources. What's this little, why do we have a duct going back to the tail? What's going to be back there? That's our APU source, right? APU is usually in the tail. We also got a couple little circles there. Those are our outflow valves. Different ventilation ducts, cooling or environmental control packs right here, and air being routed all over throughout the aircraft. This is that ATA 36 versus ATA 75 I was talking about. So we're looking basically from the pylon, roughly the pylon shutoff valve or the main pressure regulating shutoff valve, downstream of that to the aircraft side. Anything upstream of that is often on the, is going to be in chapter 75 with the engines. That actual shutoff valve, that pressure regulating shutoff valve or that pylon spar shutoff valve, usually that's included in the airframe side in chapter 36. However, some aircraft, they do put it on the engine side. So that can kind of be on, you know, when you go to find it in manuals, you may have to look in one or the other section in order to find that division point. Shown on a diagram, what we're looking at here is, you know, here's our engine with bleed air coming off of it. And here we have, you can see a firewall on our diagram. The NAPRSOV right here, that's kind of that division point. Sometimes the pre-cooler is on the engine side, sometimes the pre-cooler is on the airframe side. It just depends. Depends on where the pre-cooler is physically located. If we look at the indication and our controls for this, the schematic on a typical ICAS screen is going to look very similar. Here is that, this is what I'm talking about, where the airframe bleed air starts at that shutoff valve. You can see the shutoff valve just inboard of each engine. Okay. And those valves are controlled by, that's typically what you have control over up in the cockpit. You can see there's a couple other valves that are downstream closer to the engine, high pressure shutoff valves and check valves. Those we often don't have direct control over. Those are more something that gets managed automatically. We'll look at what those are. But here we have our bleed air shutoff valves, 1 and 2 on the left and the right. And these are going to control, so bleed air 1 right here is going to control this valve. Bleed 2 is going to control the right engine shutoff valve. Bleed APU, here's our APU, it has a shutoff valve. We have a cross bleed. Normally these are operated with the manifold split, but we're going to have a cross bleed in the middle. And then we have our pack shutoff valves here and here, our cooling packs. And then that flows into our air conditioning system shown at the top here with our temperature control knobs and then recirculation fan. So we can select our temperatures. We can turn our recirculation fans on and off. Okay. Pneumatics on most aircraft, most transport aircraft, are one of the very heavily systems. So we just got done talking about fuel, and we basically said fuel feeds the engines and the APU. Pneumatics can feed all kinds of items. What runs on pneumatics? This is one of those interconnected questions. What can you run on the pneumatic system? What have we talked? We've talked about quite a few things already. What's pneumatics used for? Used for anti-ice. What? Pneumatic motors, we'll call that starting. A pneumatic starter, air turbine starter. What else? We also can use pneumatic motors to drive other things. What are some other items that can be driven pneumatically with an air turbine motor? You guys did this in the sim with, in the sim I have to apply hydraulic, or I have to apply electrical and pneumatic for you to run it on the ground. Why do you need pneumatic on the ground? On the sim. Two of the hydraulic pumps are pneumatically driven. Okay? It can drive hydraulic pumps. What else? What's that? So we call it HVAC is buildings. ECS would be environmental control system on an aircraft, is what you're going to see in industry. Okay, same thing, different acronym, different name. ECS, environmental control system. What else? Pressurization, we just mentioned. What else? At a group yesterday do a lab in engines. I said something was pneumatically driven. What was that? The thrust reversers can be pneumatic. What else? What happens when you use the lavatory on an airplane? What do you hear when you hit the flush button? Big sucky noises, air, right? Pneumatic. So environmental control, we talked about pressurization, engine starting, thrust reversers, anti-ice, which can also be wings, tail, and or cowls, the hydraulics, fuel, thrust reversers. I have that twice. I do. Silly me. Potable water, vacuum waste. Potable water, we can pressurize a water tank to send water up to the faucets. I have hydraulics on here. So in the sim, we have a pneumatically driven hydraulic pump. What else can pneumatics be used for on hydraulics? What else could be hydraulic or pneumatically pressurized? Prevent foaming. You can have pneumatically pressurized reservoirs in hydraulic systems. Okay, you provide head pressure. So you got a lot of things that can run off of the bleed air system. Okay. So our sources, our primary source in flight is engines. We can use the APU as a backup, and then on the ground, we often have things that are called start carts, hover carts, or bottle carts. Duncan just let me know they got the hose fixed on theirs. Hopefully, maybe this summer during summer servicing, we can run the stuff on the 727 with it. But bleed air is expensive. Okay. When you turn on bleed air from an engine, when you start using it, you're going to see fuel flow increase. Okay, there's an increase in fuel flow. The engine temperature is going to increase. Your thrust is reduced. Oftentimes, bleed air, if you fly, pay attention during takeoff, you may notice that the amount of air coming out of the little gaspers over your head, the volume of air drops during takeoff. That's because when you slam those throttles forward and you need all that air flowing through the engine to keep the engines from overheating, it's going to prioritize keeping the engines cool so they don't melt over keeping you cool in the cabin. Okay. Increased wear and tear because of that heat, because of that extra, that caused more wear and tear. So newer aircraft, some of the newest aircraft, the 787 in particular, has gone to a no bleed architecture. The 787 does not have a bleed air system on the engines. It doesn't mean it doesn't have a pneumatic system, but it does not have bleed air. They don't pull air off the engines. It's actually, in that case, they've able to make it more efficient by putting bigger, more powerful generators on the engine. The generators operate electric compressors that provide bleed air for pressurization and environmental control. They don't use it for heating the leading edges, though. The leading edges are electrically heated. And I believe the thrust reversers are hydraulic, but I'm not 100% certain on that. So they call it a no bleed architecture. It doesn't mean there's no pneumatic. It just means that they're not pulling from the engines. The other spot you have that is small engines you can't pull air from as well. So bleed air, we're going to control it using various valves throughout the system. And I've got kind of three main types of valve we'll see, and then the fourth one is a combination of some of these. So the first is a shutoff valve. Shutoff valves are typically something that would be either in an open or a closed position. Okay, when they're open, air flows. When they're closed, air is shut off, hence the name shutoff valve. These can be solenoid driven with electric solenoids. They can be pneumatically operated. We use the air pressure itself to operate the valve. So they're going to typically be spring loaded one direction, and then we use air pressure with an electrical signal or even an air signal to change it. Aneroids can control the air pressure, aneroid control. And they're going to be full open or closed. We can also have motor driven versions of these. You hook in a little electric motor to it. And most of these, almost all these valves are going to be either a butterfly style or a poppet style valve. And these, when we say motor driven, open or closed shutoff valves are almost always going to be a butterfly style valve. Okay. Round tube, circular plate inside of it that can turn one way to open, can turn the other way to close. That's where it gets the term butterfly valve. Okay, it looks like the wings of a butterfly. Check valves, we've seen those, spring loaded, closed, pneumatically operated. How are they pneumatically operated? Air just pushes on the valve, right? What style are most of these, you think? Think they're a butterfly valve or a poppet valve? They're mostly a poppet style valve. Air pushes on it, pushes a spring back, allows air to flow around it. Okay. Very few also may be flapper type valves, two flaps. So, little doors that can open one way but not the other. Those tend to be more fragile. So they're spring loaded closed and then they can open to let air by. So you'll see those as well. So poppet valves or little door type valves. Okay. Then we have the next one is load control pressure regulating valves. So these can control the amount that the valve opens, and again, it's typically a butterfly type valve. But they can be poppet style as well, but most are going to be a butterfly valve. And you're going to have some kind of a feedback loop. They can be torque motor controlled if they're electric. They can be pneumatically controlled, again, using like an aneroid type setup, looking at differential pressure on two different portions of the system and adjusting the valve. And they don't necessarily have to be fully open or fully closed. They can be variable. Do that. And again, these can be motor driven as well. We just use an electric motor to position the valve more or less open. And then the last one is a combo valve. And the common combo valves you see are, and I mentioned this before, like a pressure regulating shutoff valve coming off the engine. So an engine at different speeds is going to produce different amounts of bleed air or different pressures of bleed air. And the airframe is going to look for a certain pressure, typically somewhere around 30 to 40 psi. So a PRSOV, pressure regulating shutoff valve, that can be closed all the way to shut off. But when it's open, it's going to open enough to adjust the pressure of the flow downstream of it. But it can also be used as a shutoff valve versus a straight regulator or control valve where it can't do a true shutoff position. These have the ability to shut off. Load control shutoff valves, similar type thing. Rather than looking at the pressure downstream, they're looking at how much you're taking from, say, the engine or taking from the APU. And they're going to choke off flow. If you're pulling too much air from the engine, it's and it's going to cause it to overtemp, or you're pulling more air from the APU than it can supply, it's going to choke down that flow so that you don't damage the APU or the engine through overheating. There's all kinds of different ones too. You'll see different names. So LCSOV, LCSO. You saw, some of these here. NAPRSOV. I can't remember what the NA, pressure regulating shutoff valve. I don't remember what NA means on it. You can see they just added more and more letters and acronyms. I'd have to go back and double check what that stands for. So that's kind of those combo valves. Okay. Yeah. So if we look at our valves, here is a load control or pressure regulating valve. So here is the duct with a butterfly in it. It's kind of this part right here. Is this down here? This part down here is this upper part here. And it's going to actually use, you can see it's on the upstream side of the valve. And that puts pressure on one side of an aneroid in here. You have some of that air goes up to something called a torque motor controller. This is a torque motor right here. And it then controls that, goes up, goes to the torque side based on the input. The torque motor controller is used to adjust how this valve works. So we pull it out. Here's the torque motor controller right here. Okay. And so this is that same thing. Here is, I thought I had these together. There we go. So here we get air, from the high pressure side goes to the torque motor controller. That is then, this uses, a torque motor controller uses electrical coils here to kind of vary this little thing back and forth to open or close, the flow of air. And then on the outlet side, it then routes that controlled air back to the other side of the control mechanism for the valve itself. And so in this case, this valve is spring loaded one direction. You can see the big spring there, but then we can adjust how much, how open or close this, this butterfly is with some feedback, and be able to provide an input to the torque motor controller in order to, so it's variable and we can make changes to it. Okay, it's looking at ambient pressure here. It can also look at downstream pressure. In some cases, they'll look at what the downstream pressure is if it's trying to regulate downstream pressure. By moving back and forth, we can adjust how much air is flowing to that output side. And these can move extremely fast. They can do very, very fine adjustment of valve positioning. So these are often used for those combo valves. It can be a shutoff valve. In this case, the spring kind of is your shutoff, provides your shutoff function. That's going to push the valve closed. And then the torque motor is going to adjust how much it's open to be variable in order to regulate pressure or flow.